So, yesterday we got atomic size. And if you remember, what I told you about atomic size, matter of fact, let me go back for a second. What I told you about atomic size, there he is. I'm going to use atomic size to predict all the other trends, at least to get me started on all the other trends, okay? And now here comes the first of the other trends. Let me just fix the camera a little bit so you can see it better. All right, we know what happens as we go down a group from top to bottom. And we know what happens as we go across a period. I explained that yesterday, why they do what they do, right? As we go down a group, who can refresh my memory? What's the reason this guy gets bigger as I go down a group? What's that?
Energy levels.
Right, more energy levels, not more protons, neutrons, or electrons. What's the reason this guy gets smaller as I go across? He's not adding energy levels. He's just filling up the energy level he already has. So why is this guy way smaller than that guy? Coulomb's law, which basically says the greater number of positive and negative charges, opposite charges, attract, and they're going to pull themselves closer, and very close. In that as an inverse square law, in that doubling the charge will actually get 1/4 the distance. It's going to be much closer together. All right, very good. Now you remember that from last time. Now let's use that rule. Let's use that trend, I should say, to predict metallic character. Now we can't do that unless we know what metals are. A metal is a guy who wants to lose electrons. Seriously, every time I'm teaching, somebody calls. Hello. Yeah. Yeah. Sure, I'll have him pick it up. Okay, bye. Okay, let me put this same chart we just had over there. Okay, put the same chart we just saw a minute ago up on the board over here so I can refer to it every time. While you're copying that down. All right. So what makes somebody, and this is like I hate to tell you, probably the most important trend. This guy and the next one, we're talking about these today, in the periodic table as far as predicting what guys are going to do when they form a compound. All right, that's going to be my ultimate goal. I want to eventually get to the point where I could tell you, if I give you these two elements, where they are in the periodic table, could you tell me, will they react? Will they form a compound? And if they do, what will the formula be for that compound? All of that starts with these trends, metallic character and electronegativity. All right, so if I know a guy is a metal who wants to lose electrons, let's see if we can't figure out which guys would be more easy to lose electrons based on my prior trend within a group from top to bottom. Let's see if we can figure this out. As I go down this group, okay, from top to bottom, we all know what happens with the size. I mean, if we were to draw them, we would have, like, here's hydrogen. He only has one energy level, right? One electron and one energy level. Lithium's got 2, 3, okay, and so on, all the way down to where we have 7, right? Okay, when I get all the way down to francium. So the electrons out here, or this electron here, what do you think? Who's going to be easier to remove that electron from? The guy at the bottom or the guy at the top? What? The bottom, right. Most of you were saying bottom, but I did hear a top from someone who won't be named on camera. Anthony. Anyway, no, this guy's way further from the nucleus, isn't he? What's holding that guy in there? That positively charged nucleus, right? So he's a lot further. I bet most people would predict that from top to bottom it's going to increase for the same basic reason we were talking about with the atomic size, right? But there's another reason. That's why I didn't finish that sentence. As I go down, it gets easier to remove electrons. I get better and better and better metals as I go down a group because the electrons are further and further and further away from the nucleus. That's Coulomb's law. The further away, the less the attraction. And vice versa. The closer together, the greater the attraction. But there's another reason. Check this out. When I go backwards here, Okay? Put them back up. There they are again. What else? What else? That's coming back up. If you didn't get a copy, I'll be back in a second. Not only is this electron here closer to the nucleus than that electron there, right? But what's in between that positively charged nucleus versus like these positively charged nucleuses? All these other electrons, these other energy levels in here are blocking. It's called the shielding effect. They're shielding this outer electron from the full pull of that nucleus. You see? That is the second reason why. Something called the shielding effect. So as you copy that down, all right, I've already kind of explained it. I'll explain it a little bit more. Shielding effect, the definition of it, is a decrease in nuclear attraction for these electrons that are further out in an energy level because of the inner shell electrons blocking some of that pull. So not only are they physically further away, but they're being blocked and shielded from the full pull of the nucleus. So notice how I was able to use the first trend, size, to predict this next trend, metals, metallic character. Okay, now you got all that copied. Let's see if we can't tell what happens across a period from left to right. Watch. Within a period from left to right, let's look at our periodic table again. You ready? As I go across now, let me erase this other one. So I'm going across from here to here. Let's use a different color, you can see it better maybe. All right, I start off with a potassium atom, okay? And I end up with, let's just stop at bromine, because bromine is going to be actually a better one to use than krypton for a different reason. Bromine is going to be less than half the size of that potassium atom, okay? What do you think? What's the prediction you're going to make? Do you think the electron is going to be easier or harder to remove over there? Easier or harder to remove than this electron? Harder. Harder. Everybody agree? And the definition of a metal is a guy who loses electrons. Okay? A guy who loses electrons. So this guy does not want to lose electrons. Matter of fact, everybody, did you ever notice there's a little red line running? It runs like this. It's not on this periodic table, but it's on your other periodic tables. That line separates guys on this side. We call them, don't have to write this down, non-metals. Everybody over here, they're metals. Because metals lose electrons. Guys on the left, they're larger, further away from the nucleus, more easily lost. Okay? So from left to right, you're going to get worse metals. Actually, you get non-metals. I know you're used to thinking of a metal as something shiny and malleable, ductile. That's the stuff you learned about metals. They conduct electricity, they conduct heat, and it's all true. But those are just properties of metals. The real definition of a metal isn't what he looks like. It's what he does when you put him together with another atom. Guys who tend to... And by the way, before I get to this next thing, I want to point out to you something. There's another factor involved here. One factor is the decreasing atomic size, which we just talked about, okay? But there's another reason. Can you think of another reason why these guys over here, on this side of the periodic table, would be less likely to lose electrons than these guys over here? Keeping in mind this row. They want what?
They want to be whole.
They want to be whole. They want to be complete. They want an octet. They want to be happy. And that's the kind of synonyms I'm going to use throughout the year. Everybody wants to be like these guys. Everybody wants to be a noble gas. Full outer shell. Fluorine is so close, he can taste it. He wants that one more electron. Last thing he's going to want to do is give up one. However, let's take a look at a guy like sodium. Sodium, what happens if he loses one electron to sodium? How many does he end up having? He has 11 now, right? How many will he have? Well, that's not so bad. If he loses an electron, he drops down to becoming like an octet. So he doesn't mind that. These guys over here are much more likely to lose for two reasons. One, the electrons are increasing atomic size. The electrons, as you go across, are getting closer to the nucleus, harder to remove them. But you also have the octet rule, which we talked about last chapter and defined. And you know what that means. All right. Now, I told you we'd have a lot of notes. I have one more trend to give you, but I'm not going to give it to you. You are going to give this next trend to me. Every time I touch the board, a word or sentence is going to come up that you're going to have predicted will come up. All I got to do is give you the definition of the next trend, and you'll be able to do this. Watch. The next trend is called electronegativity. I'm going to define it for you, and then you're going to give me the rest of the notes. I've been doing this for quite a while, and it really illustrates something. And I'll try to point it out to you as I do it. Electronegativity, definition, it's the attraction of an atom for electrons. This is a quick and dirty definition. There's more to it than that. We're going to learn about the more to it than that later. We're even going to have numbers associated with it. But for right now, just keep that in mind when we start talking about the trend. How well atoms attract electrons. Think of it that way. I am not going to tell you the notes for the rest of this. Now, here's my point in doing this. This is how you should be approaching my class every time you come in here. It shouldn't be waiting for me to put something on the board and then you physically copy it down and hoping that I simply don't call on you for any kind of a question. That's what most of you have gone through your whole lives like, okay? Here's what you should be doing. What's he going to write next? He's been leading up to this. What do you think's coming next? Can anybody tell me what one word is going to pop up here when I touch the board again? Based on what I've been doing for the past two trends. What do you think? Group. Absolutely. Group. I'm going to talk about what happens to this trend within a group. If I'm thinking ahead, if I'm anticipating this class, I know that's next because it was what I came up next under metallic character a minute ago. It was what came up next yesterday under atomic size, right? All right. What's the next statement going to say? And I'm not giving it to you. Think. All I want is the first part of it. In other words, I want to know, tell me the first part of it. What will this trend do within a group? Yeah, right. Go ahead. Start me off, Anthony. From top to bottom. From top to bottom within a group. Now, think. Based on that previous trend of size, what do you think happens to, what do you think is going to happen to the attraction for those outer shell electrons as you go down a group? Is it going to increase or decrease as I go down that group? Increase. At the bottom, there's going to be a stronger attraction for those electrons, or is it going to be stronger at the top? It's going to decrease, right? From top to bottom. Oh, wait, I don't want to give you all the answers. So I want you to give me everything. I wanted that to come up in parts, but it didn't. All right, so yeah, from top, you can write that down. From top to bottom, the attraction is going to decrease. It decreases. Electronegativity gets less. Now, without me giving you the answers that popped up there, why? Why would you expect, as I go down this group, from top to bottom, I have less of an attraction for that outer shell electrons than I had for the guys at the top? Think. Brandon. See, this is exactly what you are not doing. Playing with my pencil and hoping for me to call on someone else, even if the pencil's not sharp, is not an excuse. You need to be listening. What do you think?
The size of the atom.
Well, yeah, great wrong answer. Did you hear what he says? Great wrong answer. He's got the right idea. I know he understands it, but he said, here was his answer. Because of the size of the atom. What did he not say? Did the atom get bigger or smaller? You see what I'm saying? Oh, you know what he meant. I know what he meant. But he didn't say it. You can't just say the electronegativity decreases because of the size of the atom. You would have had to have said because the atom, what? Becomes larger. You got to tell me because the electrons are further away because of Coulomb's law. That is why you're not getting full credit on those short answer questions. You do, for the most part, understand the answer. But if all I say is it gets because of the atomic size, I'm not saying what the atomic size did. And by the way, is that the only reason? What's the other reason? Matt?
The shield effect.
The shielding effect is the other reason. The fact that the electrons are blocked. That is a full answer. Good, wrong answer. I'm glad that one's on tape because you never know what to expect. I like having bad answers. I want to give you one that I got from the morning class for a good, bad answer. That's probably confusing. For a good, bad answer. Here's one from the morning class. The electronegativity from top to bottom decreases because there's less of an attraction for electrons. What's wrong with that answer? Let me rephrase it again. From top to bottom, electronegativity decreases because there's less of an attraction for electrons. What did they just do when they answered that question? They simply rephrased the definition of electronegativity. Here's what that's like saying, why are you getting fat? You're getting fat. I'm getting fat because I weigh more. Does that answer the question? No, I'm getting fat because I don't exercise. I'm getting fat because I'm eating too much. I'm not getting fat because I weigh more. And these guys aren't getting bigger because they're getting bigger. They're not getting smaller because they're getting smaller. You have to say why. Do you understand now? That's the difference. All right, now, when I press the board next, what word is going to come up this time, Josh? Period. Period. That's what I'm talking about. Period. All right, good. What's going to come up after period? Tyler.
From left to right.
From left to right, it's going to do what?
Decreases due to.
Stop. You said decreases. Do you really think from left to right it's going to increase this time, right? From left to right, it's going to increase. Let's remember what's happening from left to right. What happens to the size of the atoms? They're getting smaller. So can you finish that explanation? Can you finish that explanation? Due to what? What do you think? Decreasing atomic size, and what other reason would also make them attract electrons better? The octet rule. Yeah. Decreasing atomic size, Coulomb's law, that's what it is, basically saying. And the octet rule. Beautiful. Wonderful. Now you got it. These are the ways I want you to answer the questions on the test. Not just from top to bottom it decreases because of atomic size. Because of decreasing atomic size, the electrons are closer to the nucleus, which has a greater charge, greater attraction, I should say. Okay? That's how you have to phrase these things. Okay? All right. Real quick, what trend do you think? Let's answer some questions. You don't have to copy this, obviously, but I told you every day I'm going to talk about these as I show you one. What trend is this, and what are we doing here? Well, let me ask you. What does A correspond to? These elements A, what does that correspond to in the periodic table? Be careful what you say here. What does it correspond to? Groups. I see that's exactly wrong. A does not correspond to group 1 or group 2 or group 3. What does A correspond to?
There's a noble gas.
Say the word though. I want two words, but what?
Metallic.
No, I'm not asking for the whole trend. Just A. What elements is A talking about in the periodic table? Which elements? Olivia.
Like you want like the name of the actual elements?
No. What?
Non-metals.
No, not the name of every single element. What would we call that?
Like period 2.
Period 2. Exactly.
Why is that not non-metals?
First of all, because period 2 goes across both metals and non-metals.
Oh, you're talking about the whole.
Well, I'm not talking about it. This is talking about it. These elements are.
What is X?
What is A? I said A, not X. What A is. All these guys in this bracket are period 2. Is that correct?
No.
What are all these guys over here? Period 3. All right, now that we got that down, that was hard enough. What's X pointing to? What element is that?
No. Beryllium.
Let's see. He's right here. This was 2.
I keep doing
Number
the
4.
4.
Beryllium.
Beryllium. Yes, beryllium.
Beryllium.
Beryllium. Beryllium. Correct. What guy is this? What guy is this pointing to here? 17 or chlorine. Okay. Finally, what does this trend do as you go down a group from top to bottom? It's amazing. I just said as we go down a group from top to bottom. Okay? And half of you or more said increase. That's not a group. This is a period. It's increasing across a period, but it's doing what from a group? It's going down as you go down a group. Tough stuff. Finally, which trend does this have to be? Because electronegativity increases across a period. Does metallic character increase across a period? No. Does atomic size get bigger across a period? No. So this guy has to be electronegativity. And these are the kind of questions you're going to get every day, showing you another graph. All right, let's stop there. Your homework's on the board up here. You can